All right, welcome to our first recording for Zed Decoded. Today I want to talk to Antonio about how we do async Rust. And first of all, hello Antonio.
Hey, how's it going?
Nice that you're here. So let's set the scene. Async Rust, we use it because async Rust is the way to do concurrency in Rust. I guess you can also use threads or other stuff, but async Rust is the community blessed way of achieving concurrency in Rust, I would say. And correct me if I'm wrong.
Yeah, we could start right there, I guess.
Yeah.
Yeah, like, I think,
Let's do that.
yeah, I think different people have different opinions and also like different applications have different needs.
Yeah.
I think for some applications, it's totally fine to not even worry about async and just use threads. The story there is a lot simpler in terms of you don't need to have a runtime. You don't need to, use a wait everywhere, or, you can just basically use the standard library and achieve concurrency just by spawning some threads. So, but in our case, yeah, the story is a bit different, and yeah, we can get into why that is. Yeah.
Let's do this. So you just mentioned this. We use async Rust because I guess we have to, right? We don't get away with threads. And I guess we can talk about this in the second step, but to come back to this other point, you said in async Rust you can choose your runtime. And some people might know this. Say in JavaScript, your runtime is your JavaScript engine. You have V8 or I don't know, what's another one? A bun, right? Like these runtimes that give you these async runtimes too, or event loops as they call it. But in Rust, you can pick your own, right? And I want to dive into the code and see where we basically set up our runtime. And am I right here in the main.rs or?
Yeah. It's a bit hidden away, to be fair. Like typically,
I'll follow you.
typically runtimes, for example, if you use Tokyo, which is one of the most popular runtimes, you will kind of decorate this, the main function with Tokyo main attribute macro. And this lets you kind of, turn this main function into an async main function. And under the hood, what that's doing is just like, creating an executor and like blocking on the future returned by this main function.
Yeah.
But yeah, in our case, the main function is still synchronous.
Yeah.
What we do instead is, we have this concept of an application. And so, this is the place where we kind of start integrating with the macOS event loop. And so that's the spot where we kind of, kick off this.
So this is the main loop of the app here, app run.
That's right. Yeah, that's what basically under the hood. What's happening is, we can look into it.
Yeah, I'll follow you.
We kind of call platform run. The idea with this is that the platform is a trait. So, this app struct doesn't really know which platform we're running on, and so on the Mac we're gonna have a Mac platform. And if you look here, what the Mac platform does is it literally creates an NS application. Here, like we have this static called app class, and you can see here it's a GPUI application that inherits from NS application. And so what that does is it literally just grabs the shared application, sets the delegate, some Cocoa kind of magic, and then at some point we say, okay, app.run, which, this thing will basically block for the lifetime of the entire application. It's a blocking call.
Interesting.
So that's kind of related, but it's related to how the executor and the runtime works. And one of the reasons why we need to have a custom executor.
Yeah, go ahead. Okay, so that's my question. Why? So we don't use Tokyo. We don't use what's another one? Small or
async standard.
Async standard.
That's another one.
So we don't use those. Instead, we basically build ourselves a native macOS application and use what Cocoa gives us, I guess?
Yeah, so basically, like when you create a Cocoa application, a lot of the things that you do, especially related to UI, but also interactive with the platform itself, like if you want to, just retrieve things about the current application or things about the current window, that stuff needs to happen on the main thread. And the main thread is basically the thread that, where the application was started on. And so, that's where our executor comes in the sense that, we can't just run stuff on any thread, right? We need to run, we have this concept of like, a main thread on which we run certain things. And so, I don't know, this is surfaced by the spawn method. Like when you say app context.spawn, what this does is it takes a feature that is guaranteed to run on the main thread. And you can see here, like the feature doesn't need to be sent for that reason. Like it basically will stay on the main thread. And if you see here, like, we have this notion of a foreground executor. But the main thought is of having like a custom executor is integrating with the Cocoa event loop and making sure that we kind of, they're able to do their stuff, like, process events on their front, and we're able to kind of get in the mix, right, as futures kind of get unparked and, make progress.
So if I use Tokyo, they give me an executor, and they also give me, I think Tokyo also has a spawn method, right?
That's right.
Yeah, you can spawn tasks and the whole task API.
That's correct.
And we use, like, can we take a look at foreground executor, what that is then?
So you can see here, we kind of have our own version of a task. We actually use the async task crate.
Okay.
And again, like the executor doesn't really know how things are dispatched. You can see here, like we have this notion of a dispatcher. But the idea is that, like, anytime a future is ready to make some progress, which is encapsulated by this concept of a runnable by an async task. So a runnable is basically like a spawn, like a runnable, is like a piece of computation of a spawned future. And so like anytime a future is ready to make progress, which happens, when you call wake on the waker on the futures context, we can get into what that is if you want later. But like as soon as a future is ready to be pulled again, this closure will get invoked. And once that gets invoked, we kind of say, okay, hey dispatcher, dispatch this runnable on the main thread. Meaning, I want you to like pull this future, the spawn task on the main thread, and the runnable encapsulates that piece of the computation. And so like we have, the dispatcher is the platform specific thing that
that's only this, across. Right? Like it's the this part. The rest is, you can write this yourself. This is our Zed or GPUI, our GPU based UI framework, right?
This is like the executor is a struct in the GPUI crate.
It's pretty small,
I mean that's like to be honest, like most of the heavy lifting is done by Grand Central Dispatch, which is the runtime effectively that macOS exposes. So we can take a look into that.
Let's dive. Should we follow this here, dispatcher main thread, or?
I mean that's gonna lead you to a trait. That's just a trait. So we could look at that. Like, so if you follow me, I mean, if you look at the thread, we have a couple of things. I mean, a few things, not just a couple. But you have this ability to understand whether or not we are on the main thread. To be a platform dispatcher means like exposing these methods. And so we're in the main thread. Dispatch means okay, you can dispatch this runnable wherever you want. I don't care. This you want to dispatch a runnable on the main thread. And this is about, dispatch chapter is about supporting timers. Basically like invoke this runnable after a certain duration, which is how we implement timers, timeouts, async timeouts. These other things have more to do with the test runtime, which I guess we'll get into maybe at a later point. They're basically a way of like controlling the dispatcher so that we can make deterministic progress. But yeah, you typically, I don't know how we implement, I mean, it's been a while since I looked into this, but I think if you look at the Mac platform, the way that we implement, the Mac dispatcher, the way that we implement platform dispatcher for this, you'll see that, yeah, most of these things are, tick is false, park and unpark, yeah, I'm not really sure where we're using these. We can look into that, but I think the important pieces are these 4 functions, which you can see like they're not that involved. It's pretty straightforward.
So how does this? I mean, we looked at this, but I want to look at it again. So how again do we talk to macOS here? Dispatch async from.
We're like with bindgen. So if you follow me here, with bindgen, we're kind of creating bindings for these 2 files, which kind of export all the Grand Central Dispatch magic. And what Grand Central Dispatch lets you do is like use this dispatch async function. And the idea with this is that you can kind of pick a queue where to run your runnables in our case. And so in the case of the dispatch, the one that doesn't need to run on any particular thread, it could run on any thread. Here we say, okay, hey, grab from the global queue, and I'm gonna give you like, this priority. Like I want the global queue to have this priority. But yeah, when we do it on the main thread, we kind of want to enqueue this particular work into the main queue, and so this is guaranteed to be the main thread of the application. Like it's going to be, on the other side of this, there's like the event loop, right? That Grand Central Dispatch is running, where like they're gonna process this queue of tasks, both coming from Zed and coming from macOS, and one by one they're gonna run them over and over again.
So then it looks like the concepts map cleanly. That's what's fascinating to me. So we have runnables and we have tasks in our world. A runnable is a thing you can use to wake up a task, right? Or to schedule it.
We can get into what that is. Yeah, that's like a primitive exposed by async task.
Yeah.
Which is a crate that anybody can install.
I guess what I'm interested in is from the perspective of Grand Central Dispatch. I'm looking at the signature here. What is this? Is it just a function pointer that it then calls?
Yeah, here we're just like async dispatch async f. We can F12 into it. Like it wants you to pass the queue, right? Some context. So this can be like a pointer to anything. Like it doesn't matter. Like it's basically a piece of data that you can attach to it. And then work, which is an actual function that they need to call, right? So what's going to happen here is that we're kind of leaking the runnable, like turning it into a raw pointer, and then we're providing a trampoline. And so if you look at what trampoline is just like an extern-C function that takes that raw pointer, reconstructs the runnable from its guts, right, from the pointer, and then it kind of runs it.
That's cool.
That's
very cool code.
It's surprisingly little code. I agree. But yeah, this basically lets us, kind of interweave macOS events, right? The macOS concerns with Zed provided tasks.
So why do that? Why use Grand Central Dispatch? You hinted at this earlier. You said if we're a macOS application, they want to do stuff on the main thread, or like the OS wants to do stuff on the main thread, but we also want to do stuff on the main thread.
Right. Yeah. Imagine like, say that we didn't do it this way, right? And we were like, okay, we're gonna grab the main thread, right? Like Zed GPUI grabs the main thread and kind of like implements its own queue without worrying about what macOS is doing. Well, the problem with that is that if we don't let go of that main thread ever, then the operating system has no way of like making progress on their own by, for example, I don't know, dispatching events, getting user input, via the keyboard or via the mouse. And so, yeah, we kind of, yeah, I think it's kind of necessary to do it similar to this because, yeah, we kind of want be cooperative, right? Like we want to just grab the main thread just for a little portion of time so that like, one of our futures can run, then we let go of it, and then other stuff in the queue can make progress, and then when it's our turn again in GPUI, we can again, timeshare basically on that thread.
So is that the reason, or coming from, I haven't done any native apps before on macOS, but why is the main thread so important? Is it this? Is it because, that's the one thread you have to interact with the OS, and that's how how the OS makes progress too, and you have to be mindful of it, otherwise you block stuff?
Yeah, I kind of think, there's no particular reason, you could argue that, if the operating system were designed differently, right, and it was multi-threaded, you didn't, maybe you didn't need this, but like, the reality is that, yeah, I think also for simplicity, like it is nice to assume that you're going to do certain things on one thread only.
Yeah.
It means like you don't need to have locks, right? You don't need to, like, if you're in the main thread, you can make assumptions about the logic, right? And so I'm assuming, I don't know how Cocoa is implemented under the hood, but like, I know for a fact that like most of the APIs are not thread safe. And so, yeah, they want you to call them from the main thread.
Okay.
And so, yeah, I think it kind of stems from integrating with the operating system. And I think, I'm not an expert, but I think it's kind of similar on Windows. Like I think, I don't know, certain things, are required to be done on the main thread, yeah.
Let's take a peek. Do we already have a Windows dispatcher?
That's a good question, yeah, like Windows, Mac.
Here, I got one.
Oh, there's Windows window, dispatcher.
Dispatcher, yeah.
Yeah, dispatch on thread pool.
Oh, it has a thread.
Dispatch on main thread, yeah, main sender. Yeah, it seems like we kind of, I didn't write any of this code, but yeah, I think it's,
Seems like we have our own thread pool then or something, right?
Yeah, that, to be fair, like in GPUI 1, before we kind of rewrote it, dispatching on any thread, so like dispatch on main thread was using the Grand Central dispatch, right? In the same way it's using it right now. But I think what we used to have was literally our own thread pool for, other threads. And so I think what we used to have was like, we would spawn however many threads as many threads as CPUs that we had. And kind of, again, did this work stealing queue type of thing where like each thread would kind of try to make progress on one of those runnables. The reason for using Grand Central Dispatch is that I know there's a couple. We never really tested it, to be honest, but I think like it's kind of cool to just use the operating system's API just because, now on the Mac you have efficiency cores and like maybe you could do some stuff, you could just save some battery as well.
Right, that also probably happens, right? That they throttle it down or something, or maybe...
Yeah, for background stuff, Like the main thread, I know for sure that like, has like a higher priority. Like I think you can specify several classes of quality, like QoS, and user interaction is pretty high in that priority list because you want to respond to feedback, to user input as fast as possible.
Okay. All right, so let's pop up the stack. So we have a platform dispatcher. That means that's even that's one lower level. I want one more up. I want in the executor. So from the app's perspective, we have two executors, right? We have the foreground executor, which now we know says to Grand Central Dispatch, please run the thing that I give you on the main thread. And then where is it? We have the background executor, which is
that's right
down here. That has a also small API, I guess. Spawn labeled, spawn internal.
And again, it's just using dispatch and not dispatch in main
Yes.
thread. The thing that changes, I think, and that's an important difference, is that now the futures you pass in need to be send. So, you need your futures to be able to be sent to other threads because,
Okay, so that means when I use the background executor, that's when I'm really multi-threading, not just concurrent, but I have to implement send so it can be sent to another thread.
Right. Yeah. So the send trait is going to be implemented automatically on the future by the compiler if all of its fields are send as well.
Nice.
Or I guess you could also implement it in an unsafe way. You can say unsafe impulse send on stuff. But typically like you don't even have to think about it. Basically, it's like if your future is ready to be sent to another thread, you can use this, and the compiler is gonna complain if that's not the case. And then the cool thing is also that this future, you could basically, the way that it works is that you could run a little bit of this future on thread 1, but then like the next time around the future is ready, you could run another little piece of that future on thread 5. I don't know. I think that's kind of cool. That can kind of be shuffled around and on any thread that's available to pull that future.
So how many threads do we configure this in any way? Do we say we want to
Not
use 10 threads or something?
Not on the Mac. On the Mac, that's abstracted away by Grand Central Dispatch. Like whatever the global queue is capable of, however many tasks the global queue is capable of polling at once, kind of, that's our degree of parallelism. But like the one thing that we do have is we do expose the ability to, grab how many CPUs you have. And that's for example, like if you're trying to do some kind of map reduce type of situation where like you want to, say you have 100 files and you want to search, on those 100 files concurrently. Well, I think it makes sense to spawn, you don't want to spawn 100 tasks, right? Like maybe it doesn't make much sense, especially if the work is CPU bound. So we expose this so that you can kind of control the degree of parallelism of the thing you're trying to achieve.
So that means, again, popping up, that means, where was the entry? Was it on here? There you go. We're on app. So on app, we have spawn and then we have background executor. So these are the, I've seen these in the code. These are our main APIs. You can spawn, which is on the foreground executor, or you take the background executor and then spawn on this. So can we quickly go through like when we would use one over the other in the code if we go through the references or something?
Yeah, one thing that's interesting to also note here, I think, is that you can only access the app context or the app state from the main thread. Like you can't go on a background thread and kind of read the app state. And again, this was something that we debated a little bit during the rewrite of GPUI, because initially we actually started to make the app state multi-threaded. But again, like having that safety, kind of like having the state always be on one thread is kind of nice, because you can make a lot of assumptions that streamline a lot of the code. So how do we use this? I mean, I don't know. Let's look. If I find all references, I mean, this is probably like the most referenced,
most used one of the Rust analyzer is going to take a while, I guess.
Piece of code. But we could probably, here you go. Yeah, so, I mean, I don't know.
There's
what's a good one?
Them.
Yeah, it's like, what's a good one? I don't know, load user theme and the themes in the background. I don't know, what are we doing here?
Yeah.
I mean, you can see here, like we're kind of spawning, and we create some kind of, we access some kind of theme registry. We do some async IO, so FS metadata. And then we come back, we can kind of update the context again and kind of say, okay, reload the current theme after we've loaded this stuff asynchronously. There's other places where we do, the other, use the background
But
executor.
just so it's said out loud, we use spawn when we want to do something. This is also running on the main thread, but we don't want to block on its result, right? Versus if this were an async function,
Right.
then we would, well, it sounds dumb to say, then we would wait on the block on the async function, but all the awaits where we wait on the result of a promise, they are inside this future, right?
That's right, yeah.
Function. So this is just start this, and then down here, which I thought was interesting, is we get back, like I see in my inlay hints, like the stuff up top, it returns a task, but then we say detach and log error. So that, what does that do? It says...
Yeah, that basically, spawns the task and detaches it. Yeah, so one cool aspect of tasks is that like a task is a handle to a spawned future. Yes. So it's not the future itself, right? It represents you know, a moment, basically like, the result of that future. And, you know, it may not have been completed yet. And so, one cool thing about the task is that if you drop that task on the floor, right, like you just drop it, what happens is that the executor is going to notice that the next time it pulls that runnable, it's going to notice that the task associated with that runnable was dropped, and so it's not going to make progress on that future. It's just going to drop it on the floor. And so to avoid that from happening, you know, if you just want to spawn something and like not think about it, you don't want to await it, and you don't want to kind of hold on to it, you can just detach it. You can just say, okay, I don't care about it. And then we have this like helper method, log error, which lets you kind of produce, literally log an error if the task fails. And this is only implemented, you can see here, in like for a task that returns a result of T, and where E is debug.
That's cool. So that means if I were to do this, right, and say let task equals this, put a semicolon here, then nothing would run yet, right? I just created this task, but it's not.
That's right, yeah.
So then I could, if this were, say, if this were an async fn, then I do task await, something like this.
That's right, yeah.
Then it would
I guess, if that returned a result, then you would be able to, grab the result of that future. That's correct.
All right, cool. All right, so then background thread, right? Where do we, background executor? It's more than
so there's some spots that I think are kind of interesting. Like, I mean,
interesting. I'm interested in one thing you mentioned, that you don't have access to the app state, and I want to talk about how we, what's the strategy, right? Like,
right. Yeah, typically, I mean, you can probably help me find a good spot where we kind of do that back and forth of like going to the background and going to the foreground.
Yes, but okay, so this is the background scanner, right? That's the thing that in the background, as the name implies, looks for what, like new directories or new files, right?
Right. And one cool thing about this is that, you can see here we're using this API, like the scoped API, which is kind of similar to the scoped API on Thread for the standard library. And the idea is that, like here, instead of this scope, we can kind of reference things outside, right? Because we can we can reference things outside of the scope, because we can ensure that the scope, will live for as long as those tasks run. And so what's cool is, like here you can see we have a bunch of max concurrent workers, and we're like spawning a bunch of tasks to search concurrently in these snapshots for a certain query, I guess. But like
project search,
Yeah, so like, but if you go up, right, where is this used? This is used over here. I mean, I guess this is not a great example of like going back and forth from the foreground to the background. But like, it is interesting still of like, we can spawn this future in the background, and then we can have, like basically what's cool about this API is that like from a foreground task, you can await a background task, right? And so, yeah, if you have something that needs to happen on the background, you could basically like, yeah, move all the state that's not app state into that future that needs to go in the background, do the work there, and then from a foreground task, await that background task, and then make progress from there. Yeah, it would be nice to find an example of that. I mean, here it goes. Yeah. Like here we're saying, in the foreground, like here, for example, we have a buffer, right? Yeah. And on that buffer, the buffer is a model, which is like, yeah, a piece of the GPUI app state.
Yeah.
And so you can see here, like, here we're in the foreground, we're gonna, get access to that buffer and acquire a snapshot to it on the main thread. And then like we take that snapshot and send it to a background thread where we can perform like the actual query search on the buffer. So yeah, basically we keep the main thread, as idle as possible, because yeah, anytime you block the main thread, it means for longer than 8 milliseconds, it means that you're gonna skip a frame. So yeah, we want to really hold that lock to the main thread as little as possible.
Yeah.
For as little as possible. Yeah.
So this opens. So we do this. We kick off. This is a task. I have the inlay hint here, right? So this. Well, in this case, if we already have the buffer open, then we just return a task ready, nothing to do. Otherwise, we do this, which opens it, like loads it from disk, right? Or it updates it. I think. Yeah,
I think it loads it from disk. Or I think it loads it from disk, yeah.
Does this also do a background thing, or is this on the main?
I think parts of it are in the background. I think the loading of the file and loading it into a rope happens in the background, but like...
So it doesn't matter, right? We just get back a task, and then here we say we spawn another task because we want to run a bunch of these, right? We're in a loop. So then we spawn another task in which we then wait, possibly for stuff in the background. And then we go again in the background and say, now we search through this open buffer for all the search results. That's cool.
And then, we await. So like here we're back on the main thread, and now we can kind of, talk about stuff that's on the main thread. And now we have also the ranges. Yeah.
Okay. So let's talk about, we could probably spend 2 hours on this, but just briefly, buffer snapshot. And I know you all invested a lot of time in this. This thing, buffer snapshot, is sent. It implements the send trade, right? Because it's sent into this thread. And let's talk about this. Is that cheap? Is it expensive? Is stuff copied around?
Yeah, it's very cheap because a lot of Zed's data structures are copy on write. Like by definition, acquiring a clone to, acquiring a snapshot of the buffer is like basically just bumping an arc, like the counter of an arc. And that's basically, we can go...
Yeah, I'm on the definition, right? Like buffer snapshot, it's a wraparound. Yeah,
there's several layers, but like, if you go to the deepest level, right, which is the buffer snapshot and the text, you can see here it's like, has a couple of ropes, and the rope that we have is copy on write to. Again, like if you go in the rope, you'll see that it's just a sum tree of chunk. And sum tree is like our, God data structure kind of that, again, like if we go deeper, it's just an arc around a node. So yeah, cloning this thing is really just bumping a count on the arc. Like it's just cloning the arc, which is very cheap.
But it is copy and write, right? So if I then in the background I want to modify some of it, then
that's right.
Stuff gets copied or something.
That's right. What's going to happen, and maybe we're going to do an episode just about the sum tree because I think it probably deserve it. But yeah, what's going to happen just at a high level is like only the parts of the tree, like the sum tree is essentially a copy on write B plus tree, and the idea is that any path that's touched in the process of mutating that tree is going to be cloned if there is another clone already. Like if you're the only holder of that arc, then you could just, write to it. And that's, we can look into it, but yeah, that's due to calling like arc make mute. The magic around copy on write is just like Rust kind of makes it very easy to implement. This basically gives you a mutable reference if you're the only owner of this arc, but if you're not, it's going to give you a clone of the underlying structure. And so yeah, like
in our example, like we're searching open buffers,
right,
and say we would put it on the background thread. The compiler tells us, or it would scream at us if that weren't safe. But since we only send snapshots around, we know that it is safe, so we send it to the background thread.
Right.
And if then the background thread were the only one modifying a buffer, it wouldn't even have to copy stuff.
That's right. If we are the only people like holding an arc to that buffer, we're not gonna clone. Now, in the case of a buffer, I think like the cool thing is that even if we're not the only people, right, holding an arc, like we're not gonna clone the entire snapshot. We're just gonna clone the parts of that B tree that we want to mutate. Like, so if you have, a billion things and you just want to change one character, you're just going to touch log n or, log 6. I don't know what the base of the B tree is, but only log base.
So it's classic immutable data structure. You take out the piece that you want to modify and update the references to the rest. And
that's right.
That's cool. Okay, so back up top, we were here in project search, right? Spawn, background executor. I think that's a pretty good example. I'm wondering, do we have another interesting background executor example?
Let's see. I mean, I'm running a find all references on this.
Yeah.
And seeing. Okay, here. Let's see. I mean, I don't know. This is kind of, I guess this is the scoped API, so maybe not. Sorry. Split operations, background search, diff-based tasks, serialize ops. Yeah, I don't know. Yeah, there's a lot of them.
Yeah.
But
I think the whole, do we do the LSP stuff? I guess that's all on the background thread. Right?
I think so, yeah. We can look into it. If we go in LSP, I think we use the background executor, yeah. And I believe, if you do LSP new, there you go, new internal, CX spawn, there you go, yeah. We basically, when sending the output to the LSP, we're gonna spawn a task that is in the background, and it's gonna take care of, I think, serializing the messages and
that's the handler for, I think, standard in, standard out, right, of the language server or something.
That's right,
standard in.
Yeah, outbound RX. I think, message as bytes. Yeah, basically, we try, in this particular case, we try to, offload the work of...
writing messages to the language server. Yeah.
Right. And again, it doesn't mean that, this task, for example, is going to be a long-lived task. So it's going to live for as long as your LSP is running. Well, the cool thing about it, and I guess that's what's cool about, back to the question of why don't we just use threads, right? Yeah. Is that we can multiplex on a thread, meaning it's not like we're going to have a thread sitting there idle doing nothing. We can reuse the same thread to perform all kinds of tasks that have nothing to do with each other.
So that means, we haven't talked about this, but the nice thing about async Rust is, like you said, multiplexing on a limited number of threads, and if they don't have anything to do, what this async function does is it waits for messages on this receiver, right? And it says, okay, I got a message, I'm gonna send it. After it sent this message, it goes back here, but then this is what I want to talk about. Somewhere down in the stack, in this call, a thing tells the runtime, or it talks with the operating system and says, wake me up again if there's a new message on this channel. And then it goes to sleep, right? And then it's sleep.
Right. It's not that it goes to sleep. It's more that like, up the stack. So like there's going to be, so this thing handle output is going to return a future, right?
Yeah.
And so at some point, like something is polling this future, right? And you can pull a future either by awaiting it or by spawning it, in which case like you have the executor literally calling poll for you.
Yeah.
And what's going to happen is that basically like each future is going to, call a little like a method on this future called poll, and this future is going to say, yo, I'm not ready to make progress, right? Like it's just going to say I'm pending. And yeah, whenever you return pending, that's your cue. You also pass a waker, like you said. And so the operating system will kind of tell us when it's time to kind of poll this future again, or this stack of futures. Because like, this could be a future within a future, within a future, within a future. And so we want to tell kind of like the thing that's at the top, which is going to be the executor, to kind of like wake us, re-poll this entire stack as soon as it's ready. And that's what the runnable does, all the way back, right? The waker, in the case of async task, is that, closure that is provided when creating a runnable.
So that means, here, I'm looking at small. Small is this, it's a crate right here. I have the docs up. And small fast async runtime. So it's a runtime, but it's not an executor, right?
I think those two terms are kind of interchangeable.
Yeah.
Yeah, I don't.
But what does it do for us? It's kind of, for us, it's a library / crate which we.
Yeah, I don't think we even use it anymore. I think it, like in the past, it used to be what we used for like the background threads, right? To create that thread pool.
Yeah.
And I think maybe the only thing we're using it for is to do like
Async IO.
Async IO, that's right. But like, for example, small future yield now, right? I don't, like, I think this is just vestigial. Like we could probably remove it and use an actual, a yield now that we implement. Yield now has nothing to do with small. Like it's just kind of.
It's just a future, right? Like it implements a future with a certain.
Yeah, if you follow me, I'm in there. Yeah. It's like, it's basically gonna kind of poll the future once and return pending and ask it to kind of re-poll again right away. It's just a way of relinquishing control back to the main thread to avoid starving it. Like imagine you have like a tight loop, right? For I in 0 to a billion, right? Like if you never relinquished control back to the main thread, you're literally starving it, right?
Yeah, busy loop. Yeah.
Right. So instead, what you can do is kind of like have this artificial await that says, okay, I'm gonna stop. It's cooperative scheduling, really. Like you're just saying, okay, I'm ready to, pull me again when you want. I'm gonna pause here.
So is this the classic this?
I guess right? So. Yeah.
From JavaScript.
Yeah.
Oh, I guess we had tick, right? Tick was the other thing, but yeah.
Yeah, tick is kind of,
No, tick is a different thing, right? Okay, let's talk about this. We got, let's say, 5 minutes.
Okay, it's going to be tricky.
No, we don't. Okay, so I'll link to the talk that you gave on this. But the premise is async Rest allows you to write async code, but then you switch out the executor, meaning the thing that polls these futures and that executes them. And you can write your own. And in order to test our async code, you did just that. You wrote the own executor.
Right. Yeah. Basically, if you follow me, test dispatcher. So we saw how the dispatcher works on the Mac. And we saw that, it was very thin, like we didn't do much. It was because most of the work was being done by macOS. Here, like in our test dispatcher, we actually essentially re-implement our own version of Grand Central Dispatch, if you will, but where we control exactly the execution of all these runnables. So like you can see here, when they call dispatch on main thread, what we do is we kind of push this runnable onto a queue in the foreground, right? Yeah. And when they call dispatch, I guess there's some complexity around this notion of deprioritized tasks, but like, conceptually, we're still pushing onto like a vec.
Yeah.
I think it's a vec or a vec deck, just a vec.
Vec, yeah.
In the background. And so, like that is all like driven by tick, which kind of signifies, stands for like a tick of the loop,
Yes.
right? But yeah, here you can see like we're kind of mixing background tasks with foreground tasks because it doesn't really matter, right? Like all we want is kind of like find a permutation of all the execution orders of both foreground and background tasks, so that we can kind of mix the order in which things can happen.
Yeah,
and so you can see here. Exactly. Like if there's nothing in the foreground and the background, I guess we look at this deprioritized stuff. But like here we decide, okay, do we want to run a feature from a task from the main thread? Okay, we pick uniformly in there, and we're like, okay, if we're on the main thread, then we want to grab one of these and like choose at random, pop it, and then run it. And this kind of repeats. What's cool about this is that provided that you have the same seed for the random number generator, you're always going to pick the same runnables, which means, we don't have, there's no non-deterministic things happening in our tests, so long as you use deterministic dependencies, right? You don't do an actual API call, you don't do an actual file system read, because those can kind of happen at any order at any time.
So I want to explain this to people who've never done this. So we have these tests. I'm trying to find it. Where did we put that git blame test? Oh, it was in editor git.
Oh, yeah, that's cool.
Sorry, typo blame. Where did we put that test? There you go. No.
Is it this? I think we did it in.
What was it? Blame random. There you go. I got it here.
Yeah. Okay.
So we don't have to go into details. We're running out of time, but because this is pretty cool, especially it was for me coming from Go. So what this test does is it sets up here, like, hey, we want to have like an app runtime with the test executor. Like everything is under the app runtime. This time use the test executor, which we just looked at. And we want to run 100 iterations. And then you can see here, there's a random number generator involved in here. And then what we do in this test is, here we set up a fake file system and random chars for the buffer. We insert some new lines, blah, 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 blah. And then here we do stuff. We run git blame on a buffer. We run the executor until it's done. Then here we use the same random number generator to randomly edit the buffer or execute it. Like we edit here, then sometimes we execute it or we regenerate blame, all of this. So what this does is it runs this program that's async and has multiple threads and multiple tasks running concurrently, but it runs them deterministically for a given random number generator seed. So previously when I did Go and I would run into race condition in tests, what I would do is either stare at the code and try to figure out where's the race condition, or run the test multiple times and see when it happens. You try to catch it, right? And then you run into these things. Oh, that only fails 1 in 20 times. But here, if something fails, it tells you exactly with this seed. Well, it doesn't tell you this exactly, I guess, but it says under this seed, it fails. That means with the seed, say 20, the tasks or threads are ordered this way, and that leads to race condition or failure or something like this, right? And then you can repeatedly run it with the same organization of threads and tasks and fix the test, which is really nice. That was really cool.
Yeah, it's pretty cool. And again, you can kind of, like here we're using, it's kind of interesting, like here we're using the random number generator, both for, like scrambling the order of the tasks, but also for generating random data. So we're kind of, it's all random, like the data that we produce and the order of execution of those tasks that are involved in this.
And the order is even double random, right? It's not just that we say, like in this block, this might spawn a bunch of tasks in the background, and that order is already random. But then we basically say also randomly, and now wait for these tasks to finish in that random order. And,
Right.
yeah, it's multiple levels of random here, I guess.
Right.
That's
Yeah,
cool.
what I really like about these tests is that you kind of don't even need to think about that. It's more just like, what are the invariants of my system that I care about? And then you kind of poke at the system from various angles, and you're like, okay, I want to make sure that no matter the order, no matter like the randomness, right? It doesn't really matter what the state is, so long as any sequence of operations and orders of execution of those operations leads to the same invariance,
Yeah.
which I think is fascinating.
Yeah. It's really cool. All right. We're at time. Thank you so much, man. This was
Yeah,
really
thanks.
nice.
Thanks for, it's really nice to, I don't know. I guess, yeah, we do this every day, kind of, but
Yeah, but
yeah,
it's
it's
nice to take the time. Yeah.
record it. Yeah, yeah.
All right.